Welcome to another lecture. In this lecture, we will discuss about the what is match filter, and then we will discuss match filter based signal demodulator, that is called match filter type demodulator. Then we will analyze the match filter type demodulator in time domain and frequency domain. So let us start. So first we'll discuss what is a match filter. A filter is said to be the match filter to the input signal x of t if its impulse response h of t is given by this relation: h of t equal to x of capital T minus a small t, where x of t is assumed to be confined to the time interval 0 to t. It means your signal x of t should yeah define in this interval one, like this. Outside this interval, this side should be 0. Okay, so this is x of t is input to a filter, and this is output of a filter. A filter is said to be the match filter for this input signal x of t that is confined in this interval if h of t will be equal to x of capital T minus a small t. This is definition of match filter. So in correlated type signal demodulator, we are using multiplier and one integrator, and then we sample. So in the place of this multiplier and this integrator, I want to if filter. So instead of using a bank of n correlator to generate variable means projections of RT on the n basis functions, we may use a bank of n linear filters. Okay, to be specific, that filter impulse response should be matched to the basis function, not R of t. Don't confuse. Where fk of t are the n basis function, and if signal is defined in between 0 to t, so basis function will be also in this 0 to t. And hk of t is 0 outside in this interval 0 to t. This hk of t should define in between 0 to t. Okay, so this is block diagram representation of match filter type D modulator. So we are using this match filters and match filter, and then we sample it t is equal to capital T. So output of a filter, kth filter, that is denoted by y subscript k of t, that should be the convolution of the input R of t. This is a received signal, okay, with the impulse response of kth filter. Okay, this can be written in integral form like this: integration from minus infinity to plus infinity r of tau into h k of t minus tau d tau. Okay, because If I will simplify this uh, integral, this can be starting from 0 to t, and then you have to integrate r tau with hk t minus tau d tau. Okay, hk t minus tau can be written like this. Okay, so now output of kth match filter can be written like this. Actually, your r tau is also defined 0 to t. Hk t minus suppose h tau is also defined in this. Maybe this is your waveform like this. Okay, this is your impulse response. Suppose this is okay. Outside this is also 0. R tau is also 0. First I will plot this hk minus tau reflection about the y-axis, so I will get this. Okay, if I will shift, if I want to plot hk t minus tau, that will be this will minus t minus t. If I will t less than 0, this term r tau and hk t minus tau, this product will be 0. Also, if t greater than 0, so this will be like this. T minus capital T, this is t, this is hk t minus tau for t greater than 0. So this will be, so that I have to integrate this r tau with hk t minus tau, that is a non-zero in interval where tau lies between 0 to t. That's why we are writing this. Okay, now we, at the output of these match filters should be sample at t is equal to capital T. Okay, now we sample the output yk of t at t is equal to t. So substitute t equal to capital T. So here I will substitute t is equal to capital T. Here I will substitute t is equal to capital T. Here I will substitute. Okay, so I will get this. Okay, so this t will be cancel out. So I will get this is, and this is equivalent to the rk that was output in the correlated type. Hence the sample output of filter at t is equal to t exactly same as the value of rk obtained from n linear correlators. Exactly same output. Okay, so in case of demodulator described previously, n match filter are matched to the basis functions, not r of t. So let us analyze this match filter in time domain. So we'll discuss time domain analysis of the match filter. One of the important property of the match filter is, if a signal, we are discussing one dimensional match filtering type demodulators, means x of t is a binary, just for mathematical convenience. If a signal x of t is corrupted by AWGN, the filter with impulse response matched to the s of t maximize the output SNR. Because s of t is a function of these cases basis vectors. So matching of s of t equivalent to matching of fk of t. Okay. So this is a block diagram of match filter of single branch. Okay, for one dimensional modulation, digitally modulated signal. So s of t is a transmitted signal, r of t is a received signal, and this is input to the match filter, and we are trying to match this match filter should match to s of t. Matching of s of t is matching equivalent to the matching of fk of t, because s of t is can be written as one dimensional dpsk like this. This is one dimension, so the k equal to 1. No, okay. So matching of s of t is equivalent to matching of basis function. Okay, and this y of t is output of matched filter. Okay, and then sample. We want to see that maximum output SNR. If s of t is corrupted by this AWGN, additive outgoing noise. So I will do certain assumption. The received signal RT consists of signal XT and N of T, which are N of T which has a zero mean and PSD N naught by 2 watts per hertz. Received signal R of T is passed through a filter with impulse response H of T that is defined between 0 to T, and its output is sample at the T is equal to T. Okay, so filter responds to the signal and noise component. Okay, so y of t will be the convolution of r of t with h of t. So that can be written like this: minus infinity to plus infinity to r tau h t minus tau d tau. This can be written like this. Already explained. So now substitute r of tau with s of tau plus n of tau, because rt is s of t plus n of t. Replace t with tau, so I will get this one. Multiply and separate these integrals. Okay, we'll have two integral like this: s of tau ht minus tau plus n tau ht. Because system is a filter is a linear system here, so the response corresponding to s of t will, and response corresponding y of t can be sum. Okay, so at the sampling instant t is called the signal and noise component. So at substitute t equal to capital T. So here it will be t capital T like this. So this part is a signal part and this part is a noise part. This is signal part and this is your noise part at the output of filter. Okay, now at the output of match type signal demodulator we have this y of t will be the, this is signal part is denoted as y small subscript small s of capital T. Noise part y subscript n of capital T. Okay, this is written in the signal component of output yt, and it is a deterministic nature. Yn of t is a noise component of output of the match filter, and it's a random natures. So let us define output as in a signal power divided by noise power. So in terms of statistical expectation of square of this ys of t, it is deterministic, so it will be expectation of deterministic signal is a deterministic quantity is that quantity. So expectation of ys of square of ys of t will be the ys of t square. Okay, now expectation of noise, mean of this, and this is noise power. Expectation of y1 of t square of y1 of t, this will be this. Now our objective, find the filter response that maximize the output is now defined as this. Okay, so to this, first I have to calculate noise power, that is defined like this. Okay, you can easily prove that this mean is 0. So mean is in the second moment will be the noise power. So square of y1 of t can be written y1 of t into y1 of t. Okay, and then I will write an integral form of this y1 of capital T. This is this. I am using tau dummy variable for integration. Here I am using t as a dummy variable. Multiply, okay, and then take expectation operator inside. So this is random nature. So expectation operator will work on this. This is deterministic nature signals. So expectation will be the same. Deterministic signal. Okay. So this is expectation of n tau with n t. This can be autocorrelation of this noise t minus tau, and autocorrelation of Gaussian noises can be written like this. Okay, so this is autocorrelation, and this will be this. I will substitute this, and now I will integrate with respect to first t. So using the direct after integration of this, you are integrating with t, so will be t will replace by tau, because if you are integrating a del t minus tau t minus t naught with f t dt, the result from minus infinity to t or 0 to t, because t naught is less than this. So this will be f t naught. So based upon this, I can written like this. Okay, so this is a square of h of capital T minus tau. So now we have a noise power expression like this. It is given in equation number 3. Now expression of the signal power, this is square of ys of t. So ys of capital T is this. Square this. This is square. There is some equation number is wrong. Use 3 and 4 into 2. Okay, we can obtain this, okay, by changing, because with the change of variable as for mathematical convenience, by change of variable, this is also equivalent to this h tau s capital T minus tau dt, both are equal. Okay, so I have written like this. Now recall the Cauchy-Schwarz inequality. If G1 of tau and G2 of tau are finite energy signal, then square of this integral in between 0 to capital T, G1 of tau into G tau of dt will be always less than equal to 0 to capital T integration of G1 square of integration of square of G1 of tau in between 0 to T multiply with integration of G2 square of G2 of tau in between T. Equality holds when G1 of T is C times G2 of tau, where C is a arbitrary constant. So let us assume G1 of tau is C into H tau and G2 of tau is S capital T minus tau. From our this, I am assuming this is G1 of tau, this is G2 of tau. Okay, and assuming G1 of tau is C into H tau. Okay, substitute this and apply the Cauchy-Schwarz inequality. So I will write this. So less than equal to. Now, note that 0 to tau for this one, 0 to t is integration of square of h of tau in between 0 to t. Apply the change of variable where assuming that t minus capital T minus small t is a tau. Okay, so when tau is 0, so t will be capital T. When tau is equal to capital T, so t will be 0 and minus dt will be the d tau. So after doing simplification, I will get this one because integration from t to 0 from capital T to 0, this can be written as a minus of 0 to t of this integration, and minus will be cancelled out. Minus multiplication minus is multiplied with minus will be plus. Okay, so I can write this 0 to t integration of this will be this, both are equivalent. If I use this here, so c square will cancel out and this term will be cancel out. Okay, so we have this term only. Okay, this can be written 2 by n not 0 this. So using above relation we can obtain the maximum value of this S output SNR occurs when equality holds. It means G1 of tau should be C times G2 of tau. So substitute G1 of tau is C into H tau. Okay, and this is C times G2 of tau. Okay, so this constant will cancel out. So H of tau will be the ST. H of tau equal to S of capital T minus tau. Okay, now change the variable, independent variable. Here, change here, replace tau by small t. So I can get this. So it's implied that H of t is matched to the signal S of t. Okay. Okay. So output SNR, what should be the output SNR at the equality? So this will be 0 to capital T, this integral we have to solve, change of variable apply, and I will get this one, square of this. So this is energy of signal S of t. So maximum value of the output SNR will be, this is 2 into ES by N naught. ES is the average energy of the signal S of t. So note that output SNR from the match filter depend on the energy of the waveform S of t, but not the detailed characteristics of the S of t, because it's depend on, suppose you have a signal like this, you have this, you have a signal like this, suppose like this is have different characteristics, but both have energy ES. So output SNR depend upon ES, not the shape of S of t. So let us analyze the frequency in frequency domain, this match filter demodulator type demodulator. The match filter has a interesting frequency domain interpretations. Okay, we'll get a set, because certain information is not possible to extract in the time domain. So we want to go in another domain, that is a frequency domain. Generally, we'll do in the signal analysis. So in the match filter has interesting frequency domain interpretation. So we know that since h of t equal to s of capital T minus t, the Fourier transform of this relation, calculate the Fourier transform of h of t, this will be this, substitute h of t is equal to this s of capital T minus t. Okay, now change the variable, t minus t should be replaced by tau, and then after manipulation I will get this one. Okay, exponential, after simplification, after simplifying exponential, I can write this outside the exponential because it is independent of tau. I can outside the integral. So now will this, and this will be the equal to the Fourier transform of capital S of f is a Fourier transform of this S of t. So as you know that this will be in integral form, it will be S of t into e minus j 2 pi f c t at tau, whatever you want. Okay, there is no issue. Tau d tau, because here is positive, so this plus f frequency can be treated as minus of minus f. So that's why it is equivalent to S of minus f. Because S of t is a real signal, then conjugate symmetry property holds. It implies that S of minus f will be the conjugate of S of f. Okay. So now we have a frequency response of this match type filter. Okay. That is related with the Fourier transform of the signal. So now we will Fourier frequency response. I will divide this frequency response into magnitude response and phase response to analyze the match filter based signal demodulator. So magnitude response, absolute value of h of f. I will take absolute value of a and to b will be absolute value of a into absolute value of b. Applying this, I can write this. This will be equal to absolute value of exponential minus j 2 pi f t will be 1. Okay, so this will be this, because absolute value of conjugate symmetry property, apply conjugate symmetry property, means conjugate of s of f will be the s of minus f. Okay, this will be this, and do you know that a Fourier transform property of a real signal, that magnitude spectra is even function. So this will be equal to this. So magnitude spectra of the frequency response of match filter should be equal to the magnitude spectra of the signal S of t. Okay, so this is very important observation. Now I will discuss phase spectra of the this frequency response. So h of, because I can write this h of f will be the mod of h of f exponential j angle of this h of f. Okay. Sometimes e power I am writing, sometimes exp. For convenience, I can, both are same thing. They both are representing exponential. Okay, this will be this. This can be written in this, and similarly this can be f. This also s of f can be written as magnitude of s of f into exponential j angle of s of f. Okay, so conjugate. So s of f is real quantity, conjugate will be the same. Conjugate of real quantity is same. Okay, due to conjugate the exponential complex exponential, so this will be minus. Okay, now I will compare, because h of this will be equal using this, so this will be cancel out this. So okay, now I will compare angle part of this exponential term, so I will get this one. Okay, so the magnitude of frequency response of match filter identical to the magnitude of transmitted signal spectra. On the other hand, phase of the frequency response is negative of this phase of S of f. This is phase of capital S of f. This is Fourier capital S of f is the Fourier transform S of t. So now we can write output of the this. We apply this linearity property, because your received signal will be the sum of two signal s of t plus n of t. I will analyze individually. So I will analyze, assume that this is absent. So what is the response of the output of this match filter corresponding to the this S of f? Similarly, apply this random signal, that is PSD of this. So output PSD corresponding to this. Okay, so now S of t is deterministic. So in frequency domain, output y subscript small s of f will be the multiplication of frequency response with the Fourier transform of the S of t. H of f can be written like this. So this will be this. This will be can be written as square of absolute value S of f. This will be this. So now we will use the linearity property of Fourier transform. Hence the output signal waveform ys of t take inverse Fourier transform. So I substitute this, I will this, and then I will sample the output of match filter t to obtain this, and this is equal to energy after simplification. This will be cancel out. Okay, so this is equal to the energy in frequency domain of this signal ys of t. This is signal component. Now the noise of the output of match filter has a PSD. This PSD of output of LTI system is square of magnitude of the h of f multiplied with the PSD of inputs signal. Okay, this will can be written like this. Hence, let us calculate the total noise power. Okay, from PSD we can calculate noise power. PSD is the Fourier transform of autocorrelations. So using partial theorem, I can calculate the power from the power PSD like this. Substitute S naught of F, and we know that H absolute magnitude response is identical to the magnitude response transmitted signal. Substitute this will be this. Hence, total signal power at the output of match filter is, this is square of this ys of tau. This will be this, and this is total noise power. So output SNR will be the PS by Pn naught. Substitute, I will get this. So this result agree with the result given by the time domain analysis. Okay. Thank you for watching this lecture. I am taking material from this books. You can refer this books for more details. Okay. Thank you.